Welcome back. In the last two videos, we proved an extremely important theorem which characterized Galois extensions. So let me quickly show that theorem to you. So it showed that if you have a finite extension, it is Galois if and only if it is a splitting field of a separable polynomial. So let me now talk about a couple of important corollaries of this, and they are very easy corollaries, and this is in fact some of the most important corollaries for which we prove that theorem. Okay, so one is essentially contained in the theorem itself. So let K over F be a finite extension of fields, then K over F is Galois. This is a different kind of characterization. Earlier we said it is Galois if and only if it is a splitting field of a separable polynomial. Now we are saying that K over F is Galois if and only if K over F is normal and separable. Okay, so this is the most common way of stating the previous proposition theorem, and in fact you will see this in any books on Galois theory. So let's suppose that K is a splitting field, K Galois, K over F is Galois, implies K is a splitting field of a separable polynomial over capital F, right? So this is the theorem. So let me use capital H. This is the theorem. So now this means that first K over F is normal. This is trivial, right? Because it is a splitting field of separable or not, it is a splitting field of a polynomial, so it is normal. Second, in the course of the proof, in the course of in fact this forward direction of the proof, and I noted this in fact at the end of that part, we showed that K over F Galois implies K over F separable. Okay, so let me not point out where I did this, but in the beginning of the proof of the previous theorem, we started with an alpha in capital K, and we in fact constructed its splitting field. Constructed its irreducible polynomial, and we showed that it has distinct roots. So it is separable. Okay, so if it is Galois, then it is normal and separable. The other direction is also clear. So if K over F is normal, implies by definition K is the splitting field of a polynomial. No adjective is added to that polynomial. Normality simply says it is a splitting field of a polynomial F over F. Now K over F is normal, separable, implies F is separable. Because F is every irreducible factor of F is the irreducible polynomial of some element of capital K. So F is separable. So it is a splitting field of a separable polynomial. So hence it is normal. Hence it is Galois. So that proves that a normal separable extension is automatically Galois. So several corollaries of this, maybe I called it corollary 1. So corollary 2, if K over L over F are field extensions, K over F is Galois, implies K over L is Galois. This is trivial, right? Because K over F is Galois implies K over F is normal and K over F is separable. But normality and separability is carried to a K over L. In fact, separability also follows for L over F, but normality does not follow for L over F. So K over L is normal and K over L is separable. So K over L is Galois. Let me just warn you that it is not true that L over F is Galois. normality fails, not separability. In fact, we saw an example of this, right? You have a degree 4 extension or degree 6 extension, which we will discuss later, and it has intermediate field which is degree 3, q adjoined cube root of 2 and omega, q adjoined cube root of 2 q. So this is Galois, not Galois. And finally, this is the example where we are going to let characteristic of f be 0 or f is finite. More generally, f is perfect. Remember, this means that it's either characteristic 0 or every element of f is a pth power, and characteristic is p and every element is a pth power. Then a finite extension k over f is Galois if and only if k over f is normal. Trivial corollary, because we know that Galois if and only if normal and separable. If the base field is perfect, it is automatically separable. So Galois is if and only if normal. So this is when we are, for example, dealing with only characteristic 0 fields. Galois is nothing more than normal, so that is useful to keep in mind. So let me just quickly do an example that illustrates some of the features of the proof of the previous video. Okay, so these kind of things we don't typically study in this course, but I wanted to do this for your understanding of the process in which we proved the previous theorem. Let's take this to be k to be Ct. So this is the field of rational functions in one variable over C. Remember, this means the elements are ratios of rational polynomials. They are C square bracket T and G of course is non-zero. So I'm going to look at two automorphisms of K, sigma 1 and sigma 2. Sigma 1 sends, because I want to think of C automorphisms, everything in C is fixed, but T goes to IT, I of course is an imaginary square root of minus 1. So sigma sends T to IT, sigma 1 sends T to IT, sigma 2 sends T to T inverse. Okay, so T goes to IT under sigma 1, sigma 2 sends T to T inverse. So it's easy to check for you, and these are easy exercises that I will lay for you. Order of sigma 1 is 4. That means sigma 1, sigma 1 square, sigma 2 square are all different from identity, and sigma 1 power 4 is identity. Order of sigma 2 is 2. That is even easier because T goes to T inverse under sigma 2, T inverse goes to T. Here T goes to IT under sigma 1, T goes to IT, but then IT goes to, I is a constant, so I times IT, which is minus T, that is 2 times. Third time it will go to minus IT because minus 1 is constant, T goes to IT, and finally it goes to minus I times IT, which is T. Okay, so sigma 1 power 4 is identity and none of the smaller powers is identity. So in fact the other this is easy, but the main exercise is the group, check that sigma 2 sigma 1 is equal to sigma 1 cubed sigma 2. Okay, this is a simple calculation. Okay, you just see where T goes under both direction, both maps, and show that the group generated by sigma 1 sigma 2 is the dihedral group. In fact, it is order is 8. So I'm going to use this. So I won't do this in this video. You can check this. This is a simple calculation. This is exactly the defining feature of a dihedral group. You have 2 generators. D4 has 2 generators, one of order 2, one of order 4, and the 2 generators have this property. Okay, so now use this, you prove this on your own. Okay, now I want to understand, so let's call this G. Let G be the group of automorphisms generated by sigma 1 and sigma 2. We know that it is a dihedral group and we know it has order 8. So what is the fixed field of this group? Okay, so the claim first is K is of course Ct, K power G has degree 8 because K colon K power G is the order of G, which is 8. So that is part of this exercise. In fact, that is what you want to see. I mean, the fact that it is in fact D4 is irrelevant for us. It is order 8. So now I want to understand this more carefully. So first note that take this particular element t power 4 plus t power minus 4 in K. This of course is in K. Remember, T inverse is our usual way of denoting 1 by T, right? So t power 4 plus 1 by t power 4. So then what is sigma 1 of t power 4 plus t power minus 4? So t goes to it, right? So this is it power 4 plus it power minus 4, which is of course t power 4 plus t power minus 4. Similarly, sigma 2 of this is t power minus 4 plus t power 4. So that means t power 4 plus t power minus 4 is fixed by every element of G. It is fixed by the generators of G, so it is fixed by every element of G. So that means entire is contained in the fixed field because everything in C is certainly contained in the fixed field. So we have C power t power 4, C adjoint t power 4 plus t power minus 4 is in K, is in Kg. Now we want to understand this. So what I am saying here is that this particular element is fixed by G, complex numbers are all fixed by G. So any rational function in this with complex coefficients is fixed by G. So that's in K power G. Now in order to understand the relation between these two and in fact to show that these are equal, I want to understand what is the irreducible polynomial of T which is in K over K power G. And this is the point I want to emphasize, that is the reason I am doing this example. If you go back to the previous theorem that we proved over the last 2-3 videos, this theorem, and started with an arbitrary element, we computed its irreducible polynomial like this, and I remarked at that time that this is a very useful way to find the irreducible polynomial of an element in a Galois extension. So here all you need to do is look at the image of that element under all the Galois group elements, take the distinct set of those and take x minus alpha 1, x minus alpha 2, x minus alpha r. Here of course K over Kg is Galois. In our case K over Kg is Galois. I mean this is trivial, right, because Kg is the Galois group of the Kg is the fixed field of G. So anything of the form K over Kg is Galois. That is the definition of Galois extensions. So to find the irreducible polynomial of T over Kg, let's look at the orbit of T. This is the group theory language. Orbit of T under G action. So this is the orbit, meaning where T goes under all the group elements is what we looked at. So what is orbit of T? This is easy now, right? Sigma 1, so of course T is there. Sigma 1 sends it to IT. That is sigma 1 goes to IT. Sigma 1 square, I think I wrote these things, will send it to minus T. And sigma 1 cubed will send it to minus IT. and then you have t, so you don't need to write that again, t is already there. Sigma 2 sends t to t inverse, right? Sigma 1, sigma 2 will send it to I t inverse, right? And then you will get sigma 1 of this. So here to here is sigma 1, and then again sigma 1. What do you get? I times I t inverse, so minus t inverse. And finally again sigma 1, so minus t inverse times I, right? So I, which is I minus I t inverse, okay? So this is again sigma 1. So I hope this is clear. So these are the 8 elements in the orbit. In fact, it just happens that they are all distinct. In general, remember, some of them can equal each other, but because t generates the extension here, it must have all the 8 distinct 1, 2, 3, 4, 5, 6, 7, 8 distinct elements in the orbit. So the irreducible polynomial of t over kg is x minus t, x minus it, x plus t, x plus it. So this corresponds to the first 4. Now x minus t inverse, x minus it inverse, x plus t inverse, x plus it inverse. Okay, now it is clear that you can combine these two, for example, to get x square minus t square. You can combine this to get x square plus t square, and you combine all of them to get x power 4 minus t power 4, and similarly you combine these two to get x square minus t power minus 2, x square plus t power minus 2. So you get x power 4 minus t power minus 4. But this is equal to x power 4 minus t power 4 plus t power minus 4. This is x power 8. T power 4 plus t power minus 4, x power 4 plus t power 8. Sorry, plus this is 1. Right. So this is the irreducible polynomial of this over kg. So this is correct, right? So minus t power 4 minus t power. So this is fine. So but note that this polynomial actually lives in C t power 4 plus t power minus 4 bracket x, because the coefficients are 1, which is in here, of course, t power 4 minus t power 4 plus t power minus 4, which is here, and 1 this is here. So that means, okay, now let's draw the picture again. We are almost done. You have k, which is ct, and k power g, which is a degree 8 extension, and then we have c t power 4 plus t power minus 4. Now the irreducible polynomial of t over this has degree 8, okay, because for example this is generated by, this is also kg, another way of this is kg bracket t. T is of course, t is algebraic over, so this is where things get weird here. T is algebraic over kg, right? T is not algebraic over C, T is transcendental over. So T is algebraic over this, so this is generated by T, so that's a degree 8 extension. But this, on the other hand, this is also, so basically this is also, if you call this F, this is also F bracket T. So T is also algebraic over F. C, remember, is all the way down. So all these are transcendental extensions. So these are all close to each other, but there is a long gap between these and C. This is also transcendental over C, clearly. These are all finite extensions of each other, 3 of them, but they are all transcendental extensions of C. So I am emphasizing this because this round bracket T in fact is same as square bracket T, because T is algebraic over this, T is algebraic over this. In fact, the same polynomial is, T satisfies this polynomial over F, so it is algebraic. Whereas this round bracket is not to be confused with square bracket, those will be very different, right? whereas Kg, I mean, this is something that we discussed a long time ago. Okay, so anyway, this is just to belabor the same point. So what we have is that irreducible polynomial of t over kg is this, and the same polynomial lives over this. So the degree of the extension, so these are just parenthetical remarks. So the degree of k over f is, remember, same as ft over f, because ft is equal to k. This is just like an algebraic element. T is an algebraic element over f. This ft is equal to k. So this is equal to the degree of irreducible polynomial of t over f. Right? By definition, this is the degree of the irreducible polynomial of t over f. But this is less than or equal to 8 because t satisfies a particular degree 8 polynomial. So the irreducible polynomial may be of a smaller degree. So it's at most 8. Right? This polynomial lives in fx because f is equal to this. So the irreducible polynomial of t over this could be maybe smaller degree. So it's at most 8. But this is already 8. This is already 8, and this we just concluded is less than or equal to 8. But this is some number, positive number, so this is greater than or equal to 8. On the other hand, so let me just wrap it up. On the other hand, k colon f is greater than or equal to k colon kg, which is 8. So k colon f is greater than or equal to 8. So k colon f is equal to 8. That means this is also equal to 8, but that means this is an equality, and hence k power g is equal to f, which is C adjoint. This is the statement I wanted to make because the question was find the, I don't know where I wrote that. Yeah, so in some sense, what is k power g? K power g is concretely described by this analysis. So it is C adjoint t power 4 plus t power minus 4. Okay, so this is not, I mean, this is not that important for what we do next, but I wanted to do this because it illustrates the various points raised in the previous theorem, which is an extremely important theorem. So please go over the proof of the theorem, the 2 videos, then the corollaries and the example that we just did, because these are all important features of Galois theory. And in the next video, we will start heading towards the main theorem of Galois theory. So I will first give you a couple of motivating examples, and then we will state and prove the main theorem of Galois theory. Thank you.